Hey guys, this is Princy from SVC College of Engineering. I'm going to be explaining a topic from operating system called deadlocks. So, understanding deadlocks, concepts, causes, and solutions. Introduction to deadlock, understanding the concept and its significance. Definition of deadlock: a deadlock occurs in a concurrent system when two or more processes are unable to proceed because each is waiting for the other to release resources. This condition can significantly alter system performance, making it crucial to understand and address importance in computing. Deadlock is a critical concept in computer science as it can lead to system inefficiencies and limits throughput. Understanding deadlock is essential for system designers and programmers to build robust applications and operating systems. Real world implications: in practical applications, deadlocks can lead to severe consequences such as service unavailability in critical systems like healthcare and telecommunications. This emphasizes the need for effective deadlock and management strategies. Theoretical foundations, key concepts underpinning deadlock. Concurrency in computing. Concurrency refers to multiple processes executing simultaneously, potentially interacting with shared resources. Understanding concurrency is key to identify how deadlocks can occur within systems that use multi-threading or parallel processing. Resource allocation mechanisms determine how resources are distributed to various processes in a system. That influences or pitfalls in their mechanisms can lead to deadlock scenarios if not properly managed. Process status: processes can exist in various states, including running, waiting, and locked. Understanding these states is crucial to analyze where deadlocks might arise in the flow of process execution. And then we have deadlock prevention techniques, strategies to mitigate deadlock occurrences, avoiding circular wait. By establishing a strict ordering of resource allocation, circular wait can be avoided, hence eliminating one of the necessary conditions for deadlock to occur in the system. Resource allocation strategies: implementing strategies such as resource hierarchies or limited allocation guidelines can minimize wait time and reduce the chances of deadlock forming among competing processes. Process prioritization: processes can be prioritized based on urgency and importance, allowing critical process to preempt others, thus preventing conditions that could lead to deadlock. Then we have deadlock avoidance strategies, dynamic techniques to circumvent deadlock. Banker's algorithm: a resource allocation and deadlock avoidance algorithm that dynamically calculates safe and unsafe states to ensure resource allocation does not lead to deadlock situations. Safe versus unsafe states: in the context of resource allocation, a safe state assures that there is a sequence of process that can complete without leading to deadlock. An unsafe state is one where such assurances cannot be made. Dynamic resource allocation: adopting a resource allocation based on current state of the system enables flexibility in management and reduces the chance of entering deadlock conditions. And then we have deadlock recovery methods. Measures for overcoming deadlock situations: process termination, resource preemption, rollback mechanism. These are the three measures. So process termination, one of the most direct methods to recover from deadlock is to terminate one or more processes involved in a deadlock scenario to free up resources and allow for continued operation. Resource permission involves retrieving resources from processes, potentially leading to them being rolled back to a previous state, thereby elevating and weighting alleviating and weight and restoring system flow, rollback mechanism, and systems that support checkpoints or previous states processes can be rolled back to a point before deadlock occurred, thus allowing for recovery without full termination. So these were the measures for deadlock recovery methods, that was process termination, resource permission, and rollback mechanism. Next, we have case studies of deadlock, analyzing real world deadlock scenarios, real world examples, impact analysis, and lessons learned. Real world examples, numerous high profile systems have experienced deadlock, such as databases or disturbed file systems, where operational health has serious repercussions, prompting intensive study. Next, we have impact analysis, analyzing the impacts of deadlocks such as financial losses, loss of consumer trust, and operational inefficiencies, providing insight into the criticality of effective deadlock management, lessons learned. Each deadlock scenario provides valuable lessons on prevention measures and recovery strategies that can be documented and implemented in future system designs. That's the last slide, guys. Thank you for watching.